I'm going to talk with you about time literacy. And this is a challenge that we face as geologists because geology is very much the science of time. And I've tried to work with how to explain time to students, to my colleagues, to civil society. And what I've learned a few things. Firstly, it's super important. If we're going to take on the climate crisis, we really need to understand time. And secondly, it's really, really hard. So what I'm going to do is I'm going to share a couple of metaphors I use, and I hope that you'll find them to be helpful. I want to begin here, and this is a map that one of my students drew for me. It's a map of Scandinavia. You can probably make out Sweden, you can make out Norway, the mountains. You can maybe make out Denmark, and you can even see the UK if you want to look that far to the west. But the Baltic Sea isn't there. And where the Baltic Sea once was, there was a river, and that river is called Eridanos. And it's fabled that that river would carry the amber down from the forests that were once where the Baltic Sea was. And if you were to walk on the shores of southern Sweden, you can pick up pieces of that amber. And that amber comes from trees that occupied the Baltic Sea roughly 4 million years ago. So why do I show you this? I want you to see that the world was very different 4 million years ago. And I also want to put that in some context because if I think about climate change and I think how long it would, the climate change that's happened in my lifetime, driven by human emissions of carbon dioxide to the atmosphere, and I was to think of the natural processes that put the same carbon in the atmosphere, it would have taken 4 million years. So in many ways, we can think that in terms of climate change, we have lived for 4 million years. We have lived since from the time when there was no Baltic Sea and the mighty Eridanos flowed down from Sapmi to the North Sea. Now, to understand the lecture I'm going to give, and I'm going to need to begin with some basics, some definition of some terminology, and I'm going to give you a little bit of basics about climate and about carbon. And if this is stuff you already know, well, you're just going to have to chill out and live with me at the moment. I want to make sure we're all on the same page. So, right, let's get started. Climate. Earth's climate is controlled by three factors. That is sunlight, albedo effect, and the greenhouse effect. And we really need to understand those three factors. So let's dive in. Let's start with sunlight. I find the most illustrative way of explaining how these concepts is to get some help from my cats. So I'm going to introduce you to cat number one. This cat is called Charlotte. Irrelevant. Her name is completely not part of the story. The fact that that name comes from a distillery on Islay is also not part of the story. She's a cat. She likes to be warm. So how does she deal with that? She sits in the sun, and sunlight warms the cat. Now that's really quite interesting. We stop and think about it. That means light is energy, and it's warming the cat. And we know it warms the cat because the cat radiates heat back to us. And you know that if you pat a cat. And that's roughly what happens with the Earth. Sunlight warms the Earth from very cold, which by the way is minus 270 degrees, temperature of outer space, to 6 degrees. And the Earth radiates that radiates that energy back into space as heat. So it receives sunlight, radiates heat back, converts it. However, it doesn't receive all of the sunlight that reaches the Earth, doesn't actually increase the Earth's temperature because some of it gets reflected straight back into space, and that's the albedo effect. Now, this is those of you who are good with cats will have worked out this is a different cat, but it's white. It's just like it. This is Ellen. This is Charlotte's sister. Now, Ellen's white, so Ellen reflects sunlight. That means that when a sunbeam strikes her, it bounces back off her and into the room. That white fur is increasing the cat's albedo. This is the albedo effect. So that particular proportion of sunlight doesn't change the temperature of the cat. It just gets reflected back into space. Now, what that does is for the Earth, it lowers the temperature of the Earth to minus 18 degrees. That's because large parts of the Earth's surface are fairly bright colored. Even the polar ice caps are the same color as my cat. Earth's temperature isn't minus 18 degrees, so that's where the third factor, the greenhouse effect, comes in. And in many ways, we can think of the greenhouse effect like a blanket. Here is, those of you who are good with cats will work out this is cat number two. That's Ellen. Absorbs some energy from sunlight, not all of it because of her high albedo, and is radiating heat back into the room. Well, of course, the cat wants to maintain some of that heat because it makes it happy and warm cats are happy cats. So it creeps underneath a blanket, and then that heat that's radiated off the cat is some of it's sent back by the blanket to the cat. Some of it gets released into the room anyhow. So that leads to a happy cat, which is why cats underneath blankets tend to purr. The greenhouse effect works roughly like a blanket. It warms the Earth to 14 degrees. Of course, Earth's blanket's a little bit more complex. Earth's blanket is its atmosphere, and that's a very special blanket because it's see-through, it's transparent. It lets sunlight in, and we know that because we can see the sun. But the Earth then gets its temperature rises and it radiates heat back, and that is trapped. And it's trapped specifically by greenhouse gases. And the strength of that greenhouse effect is controlled by the amount of greenhouse gases. Most importantly, for what we're going to talk about for the rest of this session, carbon dioxide and how much of that's in the atmosphere. Now, that's actually controlled. The amount of carbon dioxide in the atmosphere is controlled by three carbon cycles. And that's right, there are three of them. In fact, there's more. I'm only going to tell you about three of them. And they're operating importantly on very different time scales. Now, those carbon cycles are with what we call the biosphere. Let's just put that simply, plants, vegetation, stuff like that. The hydrosphere, oceans, and the geosphere, rocks. So, how does that work? Well, let's start with the one that we're most familiar with. That's going to be carbon cycling with the biosphere, with plants. Now, this is a playoff between living and dead plants. Living plants take carbon dioxide out of the atmosphere through the process of photosynthesis and convert that carbon dioxide and some water into carbohydrates, which make up plants. And this stays there until, of course, the plant dies. And when the plants die, they decay. And during decay, they return that carbon dioxide to the atmosphere. So that's a carbon cycle involving the biosphere. Now, if we think of it, trees, well, they live tens of years, maybe even hundreds, but let's take a sort of standard. It's the time scale that that's operating is tens of years. Then we've got carbon cycling with a hydrosphere. Now, this is in many ways slower, in some ways little at the same speed. So what's happening here? Carbon dioxide in the atmosphere is ending up getting dissolved in the oceans and forming carbonic acid in the oceans. So that makes the ocean a little bit acidic. And then there's a bunch of chemistry that happens where that can turn into bicarbonate and be stored in the deeper parts of the ocean. So bicarbonate is an ion made of carbon with carbon, oxygen, and hydrogen in it. Now, that carbon dioxide does get returned to the atmosphere by degassing. Because of that deep ocean storage, this is actually a much longer timescale process. We can think of hundreds or even thousands of years for that process to be operating. So that's carbon cycling with the hydrosphere. We're talking now hundreds of years rather than tens of years. And then we've got carbon cycling with the geosphere, and that involves rocks. And I'll introduce you to two types of rock. One is granite, which is pretty boring standard rock. Most of Sweden's made of it. And the other is limestone, and that's the one made of lots of pretty shells. So carbon dioxide is absorbed from the atmosphere through a chemical reaction whereby granite dissolves, or when rocks dissolve, we call it weathering. And the weathering then takes that carbon dioxide running through the granite, and it comes out also as this iron bicarbonate, which ends up carried by rivers to the ocean, where it reacts with calcium and makes limestone. And there it's going to remain for a very long time. That can be millions of years until that limestone ends up in a volcano and the carbon dioxide gets erupted back into the atmosphere. So this is at least, for the weathering, it's at least thousands of years. For the geological parts, you can be talking millions of years. So carbon cycling through the geosphere is very, very slow. The reason we need to know about these is a classic misconception is that when we take coal and burn it, we're affecting the biosphere, carbon cycle. But that's not actually part of the biosphere at all, because that coal is made of rock. It was biosphere from the ancient past that's been removed, stored in rocks, and then so when we actually start burning fossil fuels, we're kind of behaving like volcanoes, and we're contributing to this geological carbon cycle with the geosphere. And that's all, and that's a bit of a problem because we're not doing that over timescales of thousands of and millions of years. We're doing it over tens of years. So we've got a timescale imbalance. So let's dig deeper here. The carbon side, so what we're talking about is carbon dioxide is added to the air by volcanoes, and that's happening at a more or less constant rate if we average over geological time. And the counterpart of that is that carbon dioxide is being removed by the weathering of rocks. And that's at a variable rate. And it's really, really clever. Chemistry responds to temperature in a way that means that just the right amount of carbon dioxide is being removed from the atmosphere to keep a nice, stable climate. Um, and that I hope you're now getting that weathering means rocks dissolving because that rock's just gone. Right. So, and that is that weathering cycle. That playoff between volcanoes and weathering is the real reason that the climate's been stable on Earth for 3.5 billion years. And we know it's been stable because there's been living things on the planet for 3.5 billion years, and there wouldn't have been if the climate had not been stable. So that's the science that you need to understand. So, and I've just thrown masses of numbers, billions of years, thousands, hundreds, tens, and it's really, really baffling. So let's try and see if we can grasp what we mean by something like 3.5 billion years. And this is where I'm going to take you for a story. I'm going to share a metaphor with you about climate and time. But just before we dive into that, let's just think a little bit about what we actually say about climate in society today. If you were to Google the word climate and find out what it means, this is what you get. You get from the World Meteorological Organization that climate is the average of weather expressed by factors such as temperature and rainfall in a certain place over 30 years. And that's not a very geological concept at all. The last slides I was telling you, geology was steering the climate, not on a timescale of 30 years, it's not. Um, and that presents us with a problem straight away because the climate's changing. We set up this idea of a climate normal, and this is a really good one. This shows when winter starts in Sweden. And I'm just going to, and it's kind of contoured for the first day of winter. Winter has a definition in Sweden. I'm not going to go into that. It really doesn't matter how we define winter. But in the time period 1961 to 1990, 30 years, the average start of winter was the 1st of December. But now when we look at our climate, our 30-year average, if we take another one, 1991 to 2020, we see that's all changed. And in Stockholm, winter starts on the 15th of December, 2 weeks later. So this meteorological concept of time, of climate, has problems because the climate is changing very, very fast. So meteorologists are trying desperately to grasp with the speed of change. Let's look at another definition of climate, and this is from Aristotle. It's from 350 BCE. Aristotle divided the known world into 5 zones called climes. There were 2 frigid climes corresponding to the polar regions, an uninhabitable torrid climb corresponding to the equatorial region, and between them were 2 temperate climes which were neither too hot nor too cold. Well, this is amazing because what Aristotle is talking about is geography. This is a geographic term. You can actually map it out. You can map out climate. This map shows the yellow area in the middle, that's the torrid region. The green areas, those are the temperate region. Those are where it's neither too hot nor too cold, and the blue ones are the frigid parts. So you can actually map climate out, which means it doesn't change at all. It means there's a permanency in the word climate, which is completely in contrast to the meteorological definition. And what about a geologist? Well, this is from a paper about Jurassic climate. I chose the Jurassic because we all love it. It's full of dinosaurs. During the Jurassic, the world was predominantly warm, with at least 4 times the present level of atmospheric CO2. During the Jurassic lasted for tens of millions of years. We're talking about a climate. And this is the geological concept of climate. So here we've got climate now from Aristotle's permanent geography, geologists tens of millions of years, meteorologists 30 years, to the scary way that the climate is changing at the moment, that even comparing batches of 30 years is we're seeing differences. So we absolutely have to grasp this. So let's look at two contrasting timescales: the climate crisis, where we're observing winter happening 2 weeks earlier in Stockholm, Sweden, over just 30 years, and geological time, the timescales at which climate should be changing. So let me share a metaphor with you to express what geological time actually means. And it's going to be a paired metaphor, and I hope it helps. And the metaphor begins on the beach, and it begins with me, a geologist, sitting on a bench overlooking a beach in southern Sweden. And I'm looking out across the sea, and I'm looking at the moon, and it's a beautiful still night. And I can see the moon reflected in the water below. And it's utterly beautiful. But there's an issue here. You see, I'm not actually seeing the moon. What I'm actually seeing is what the moon looked like 1 second ago. And that's because, despite the fact the moon is so far away, it takes a second for sunlight reflected off the moon to reach us here on the Earth. It's 300,000 kilometers away, and that's how far light travels in a second. So, in a second, you can count it. That was a second. It actually is a real appreciable amount of time. This is the beach I was sitting on a bench looking over in the daytime. It's beautiful. And if you look, and here I'm standing just above that beach and I'm looking at the sun, but I'm not seeing the sun. What I'm actually seeing is what the sun looked like 8 minutes previously. Because it takes 8 minutes for sunlight to travel through space to where I'm standing on a beach in the south of Sweden. And that's because the sun is so far away, despite how fast light moves. Now, 8 minutes is certainly appreciable. I'd started this lecture 8 minutes ago, a bit more than 8 minutes ago, and then we had some technical difficulties. Okay, if we look further out into space, we can see our next nearest star. The sun's our nearest star, and that's a star called Proxima Centauri. Now, when we look at our next nearest star, we don't see it at all. What we see is what that star looked like 4 years ago, because it takes 4 years for light from that star to travel through space to where we are here on planet Earth. Now, 4 years is really an appreciable amount of time. Try and imagine now what the world was like 4 years ago. We were midway through the second wave of the corona pandemic. The war had not started in Ukraine. We had just begun a new presidency in the United States, perhaps a better one than the current one we've started. It was a very, very different world 4 years ago. But if you were in a spaceship, your Proxima Centauri, that's what you'd actually be seeing. You'd be seeing the world on the 3rd of February 2021. If we now look further afield, we can see our next nearest galaxy. And this is a beautiful galaxy called Andromeda. And I've chosen it for two reasons. One, because it's beautiful, and the second, because we're not seeing it at all. Instead, we're seeing what it looked like 2.6 million years ago, because it takes 2.6 million years for light from our next nearest galaxy to travel through space to us on Earth. And why does 2.6 million years matter to me? Well, that's when the Ice Age began. And we often have this flawed understanding of geology, and we think that the Ice Age the Ice Age has ended. Well, it hasn't. We live in an Ice Age. We live in an Ice Age that began 2.6 million years ago and is characterized by repeated glaciations and interglacials. And we live between two glaciations in an Ice Age that's been ongoing for 2.6 million years. And we are an Ice Age species. We actually thrive in an Ice Age, which is worth bearing in mind before we end it. With the help of one of the most powerful telescopes on Earth, the Hubble telescope, and with the help of a process called gravitational lensing, which magnifies the outer parts of the universe, we can see Earandel. And Earandel is a very, very distant star. And we're, of course, not seeing it at all. What we're actually seeing is what it looked like 12.9 billion years ago, shortly after the Big Bang. Um, and then, of course, we're left with a fascinating question. A typical star like the Sun lives for 10 billion years. Well, Erandel's a much larger star. Its lifespan would only be millions of years. What we can be fairly certain about is although we can see Erandel, it's not there anymore. So vast is the universe, so enormous is geological time, taking us from the Big Bang 13.8 billion years ago, passing the birth of the Earth at 4.6 billion years, to the moment that you're sitting wherever you are in the world participating in this online lecture. It's impossible to grasp 4.6 billion years. When you were a child, up until about the age of 9, you could fantasize about dinosaurs and the past in a way that we can no longer do as adults. I could talk to you about walking with dinosaurs and you could be there. That gift leaves us when our childhood comes, fantasy years come to an end. So we need analogies, and I'm going to use one now, another metaphor where I'm going to represent the Earth's 4.6 billion years with a single day, starting at midnight on the first day with the birth of the Earth and ending at midnight on the second day, with this moment where you are here and now. And at midnight on the first day, the Earth was a very unpleasant place. It had almost no atmosphere, which meant it was being bombarded by meteorites from outer space. It had no continents and no oceans. Its surface was a glowing magma ocean. And for that reason, there are no rocks, so we know very little about it. Almost nothing has been preserved. When I look at the landscape closest to me, I need to travel to the area called Sapmi to find some of the absolute oldest rocks I can find in the place we now call Sweden. And what I find if I travel to the north of Sweden is I see no rocks at all because everything's covered by a thick layer of sediment left behind by the last glaciation. But with some pretty sophisticated geophysical equipment, we can see through that layer and we can see that world that was once there. And that world was a world that consisted of tiny continents, no bigger than the island of Gotland, which is in the middle of the Baltic Sea, which is where Aridanos once was. And so the world consists of masses of small continents and one vast world covering ocean. This is what the world looked like 2.8 billion years ago at 12 minutes past 9 in our geological day. And life is already here. We already have living organisms. They photosynthesize in a different way. That way produces sulfur rather than oxygen. But then all that changes roughly 2.5 billion years ago. Some of those photosynthesizing creatures start producing oxygen. And this leads to the rise of oxygen in the Earth's atmosphere at about 2.5 billion years ago, about 10 to 11 in the morning of our geological day. And that changes everything. What you're looking at here are a green color of the cyanobacteria, which was those first living forms producing that oxygen, which by the way killed the ones that produce sulfur, causing the first mass extinction. And those kind of brown things are mounds left behind, which are the fossils that we find that we know that they were there, they're called stromatolites. Um, Moving forward in time, all the small continents bang into each other and collide and build one supercontinent, and that continent is called Nuna, and that existed 1.8 billion years ago at 2:30 in the afternoon of our geological day. So we've now got all our continents collected together. So this isn't Pangaea. This is far older than Pangaea. And then we enter a time which we know very little about, so we simply call it the boring billion. A billion years of plate tectonic quiescence. We don't know what's going on very much, but we do know we come out of that time, and we come out of that time 800 million years ago, still one supercontinent, but with a new name called Rodinia. It's already evening. It's already 7:45 in the evening of our geological day. This turns out to be a perfect configuration for global cooling, and the Earth cools down enormously. It cools down so much that it freezes over entirely. And 716 million years ago, we enter a time called Snowball Earth. This is 8:15 in the evening of our geological day. The Earth is covered in snow and ice, and there's no weathering, so there's no way of taking CO2 out of the atmosphere. But volcanoes are alive and well, and they pump the atmosphere full of carbon dioxide, And that eventually melts the snowball 635 million years ago at 20 to 9 in the evening of our geological day. Snowball Earth could be envisioned as a like a restart, like restarting your computer. It did the same when it doesn't work. Like I had to restart Zoom earlier on in this talk because things weren't working. And it did the same with life. Life restarts, and then it starts in a completely different way, with a wondrous time called the explosion of life, 541 million years ago at 10 past 9 in the evening. And this is when all those wonderful fossils that you've collected started to form. Those ones you've got at home on your mantelpiece, even if you don't admit it, I'm sure you have some. They're all post-explosion of life. Life starts in the oceans and then it moves on land. And as it moves on land, that's when the first plants evolve. And when those first plants evolve, the Earth, for the first time in its 4.6 billion years history, it becomes green. The plants live and die, and as they die, they turn into peat, and the peat gets buried. And as it's buried, it turns into coal, and that coal starts accumulating. And that's about 359 million years ago. Coal starts accumulating at 6 minutes past 10 on our geological day. And it continues to accumulate, and it has done so since then. So all that coal, all those fossil fuels we burn have been accumulating for 359 million years. And through all of that time, we haven't met a single dinosaur because their history doesn't start until 228 million years ago, 12 minutes to 11 in our geological day. They arrive on the planet. They're here for a good length of time, and reach an order of 150 million years, but their time comes to an end 66 million years ago, 21 minutes to midnight, when a meteorite hits the Earth and causes the fifth mass extinction. And our story continues as we move forward in time. India collides with Asia, and there between the places that will become Kathmandu and Ulaanbaatar, a great mountain range rises. This is the Himalaya. They were born 50 million years ago, and that was at 16 minutes to midnight. For a bunch of reasons, which I'm not going to go into, the rise of the Himalaya led to global cooling. The Earth became much cooler. It became so cold that glaciers formed in Antarctica 35 million years ago at 11 minutes to midnight in our geological day. The high reflectivity of that glaciated continent cooled the Earth some more, and the temperature dropped, and ultimately the Arctic Ocean also froze over 2.6 million years ago. That is 1 minute to midnight on our geological day. And that's when the Ice Age began. Do you remember Andromeda? That last minute is what you would see if you were in a spaceship at Andromeda, looking back at the Earth. You would see the start of the Ice Age. All I told you would have been before that time. And in all of those billions of years, I have not mentioned humans because we haven't even arrived yet. The rise of humans comes much later. That comes at 6 seconds before midnight. And humans emerge on the earth, and humans separate themselves from nature in a very perilous way, whereby we can start talking about things like natural resources and we can start treating the land around us as an enemy, something that is to be manipulated. And we can look at the land and we can look at it and say, if it doesn't produce what we want it to produce, we will make it do so. And we do that by spreading minerals on the soil, phosphates, which we mine in the north of Sweden. We spread those on the ground to make it more fertile, and we grow more crops where we want them. And that is the agricultural revolution that happens at 6 milliseconds before midnight in our geological day, which began in Sweden at this house, this ancient, beautiful house called Svaneholm, where the initiation of the way of thinking of the agricultural revolution started. And of course, the agricultural revolution means we can be more people, and that means our population grows, and it does. And as our population grows, we expand our reaches to the frigid regions, as defined by Aristotle in his Klima of 350 BCE. And as we live in colder and colder parts of the world, we need to keep ourselves warm. So we burn stuff to do so. We cut down the trees and burn them. And when we run out of trees, we dig up the peat and we burn that too. And when we run out of peat, we search underground, and that's when we find that fossil coal that's been collecting there for 359 million years. And we also find that that fossil coal is a powerful energy source and we can burn it. And not only can we keep ourselves warm, we can drive machines with it, we can drive trains, we can drive the Industrial Revolution. And that Industrial Revolution kicks off at 5 milliseconds before midnight on our geological day. And then, of course, we find oil and natural gas. And the problem is as we burn them, we're burning them too fast. We're burning them faster than the weathering rocks can remove them. And therefore, carbon dioxide accumulates into the atmosphere. And that is the root of the climate crisis, which began 1 millisecond before midnight, defined by the start of the Great Acceleration in roughly 1950. So our last millisecond, 1 millisecond before midnight, that is the climate crisis framed in geological time. And I want to close with a different way of looking at time. I want us to, the Aborigines in Australia refer to moving backwards into the future, facing our ancestors, which is why I show this picture of a tree. And this is not an ordinary tree, it's an oak tree. It's a beautiful oak tree, which was planted in 1831 by our ancestors. It was the ancestors of Sweden, and it was planted for a purpose. It was planted for the purpose of building ships. It was planted among beech trees because beech trees shade out the light, which makes the oak tree grow straight and tall. And then, of course, moving forward in time to 1975, when it's harvest time, we never harvested these oak trees because ships are now made in metal, so we don't need to harvest the oak trees. But our ancestors thought of us. Our ancestors planted trees for us. And they planted trees so that our future would be better. And this way of thinking, moving backwards into the future, facing our ancestors, is an interesting way of thinking about the climate crisis and how we find climate change solutions. You see, our ancestors planted seeds to make oak trees for us so that we could build ships in the future. We now sow seeds, and when we're solving the climate crisis, for the children of the future. And that is what thinking about time is all about. Thank you very much.